I want to talk now about the height of the tree and the number of keys in the tree and so on in a B tree. Okay, so let's use the n as the number of keys in a B tree. Okay, and let's try to reason about this and relate it to the height of the tree. So I will now draw a tree, and let's talk about the depth of nodes in that tree. Let's talk about the number of nodes at a certain depth, and let's talk about the number of keys at a certain depth. So when we start with the root has depth 0. Okay, the number of nodes there is 1, right, for the root, and the number of keys is it's not exactly, but it's at least 1. Okay. Then we go from the root to the children. If it has 1 key, it has to have 2 children. If it has 2 keys, it has to have 3 children, and so on. So at depth 1, we have at least 2 nodes. Each one of these 2 nodes has to have at least t minus 1 keys. So the number of keys is at least 2 times t minus 1. Okay, where did the t minus 1 come from? It's a property of B trees that every node has to have at least t minus 1 keys. Okay, again, I repeat, the root has at least one key, therefore it has to have at least 2 children. So now we go to the second depth here, depth 2, and how many children there we can have? We can have at least 2t children. Okay, why do we have that? Because we have at least, every node has to have at least t minus 1 keys, and when you have t minus 1 keys, you have to have t children. Okay, and each one of these nodes will have at least t minus 1 keys. So now we have at least 2t times t minus 1 keys. Okay, and we can now repeat and so on for depth 3. Now we have at least 2t squared nodes, and each one of them has at least t minus 1 keys. So we have at least 2t squared times t minus 1 keys. And we can repeat now, and we talk about what about nodes at depth h, which is the height of the tree. We will have at least 2t to the h minus 1 nodes here, and each one of them will have at least t minus 1 keys. Therefore, we have at least 2t to the h minus 1 times t minus 1 keys. Okay, so now if I say what about the number of keys in the tree itself? Well, the number of keys has to be this number of keys n, has to be at least 1, which is from the root, and it has to be at least the 2 times t plus t minus 1 from the nodes at depth 1, plus 2t times t minus 1 all the way to 2t to the h minus 1 times t minus 1. Okay, so this comes from this analysis that I showed above. So here, what we just wrote here, this is 1 plus, this is 1 plus 2 times t minus 1 multiplied by, let's talk from I equals 0 to h minus 1 of t to the I. Okay, so if you look at this, when I is 0, then this is 2 times t minus 1. When I is 1, 2 times t minus 1 times t, and so on. So this is really what we have there. And if you look at this, we have the geometric series, or this is the sum of numbers in a geometric series here. And in Comp 182, we talked about sums and series and so on. And just as a reminder, that if we have a geometric series of the form a r to the k, and k goes from 0 to n, a formula for this sum, and you can actually establish it using, again, the perturbation method, is a r to the n plus 1 minus a divided by r minus 1. Of course, r should not be equal to 1 for this formula to hold. Okay, so if I make use of this formula here, what I get is 1 plus 2 times t minus 1. And this summation here, the t to the I, the summation from I equals 0 to h minus 1. So if you want to make use of this formula here, notice that the a is 1. And the r is basically the t in our case. The k is the I in our case. And the n is the h minus 1 in our case. So if we do this here, what we get is 2 times t minus 1, and the sum here will be, based on that formula, will be t to the h minus 1 divided by t minus 1, okay? This one. So now if I cancel out the t minus 1 here, what we get is 1 plus 2 times t to the h minus 1, okay? So now let's look at it here. What we have is n greater than or equal to 1 plus 2 times t to the h minus 1. If I just keep t to the h on one side, I want to keep t to the h here on this side, then I can now push the n minus 1 over 2 plus 1, like this here. And this is basically n plus 1 over 2, okay? So we have t to the h is smaller than or equal to n plus 1 over 2. If I take log base t for both of them, what we get is this. And this is the important result we want to get. What does this say? That a B tree with n keys and whose height is h and has minimum degree t. Again, for this t greater than, the degree here is the number of keys. Again, we have the t. So I'm talking about a B tree. It has n keys, it has height h, and it has that parameter t. It satisfies that h is smaller than or equal to log base t of n plus 1 over 2. Okay? And this is a very important result about B trees, because now if you think about it, as the larger t is, the smaller the value of the height, and the smaller the number of discretes that we have to apply. Of course, if the t is very large, this can cause some problems as well, because if t is small, let's say like for binary, so we talk about a sparse index. Again, remember that the index is the tree structure itself. So we're talking about sparse index here, and it requires little amount of memory. Okay, but if t is large, then we have a dense index, and this could require more memory here. But one of the issues with also large index is that when we talk about the node having somewhere between t minus 1 and 2t minus 1 keys, again, 2t minus 1, if we take 10t to be, let's say, if we take t to be 1000, so we are talking about somewhere between 999 and somewhere between this number of keys. So we could define, a node that has 999 keys, or go all the way to almost 2000 keys. So we can have lots of nodes that have close to 1000 keys, and basically we are wasting so much space there because we are not utilizing anything with these keys there. Okay, so choosing the value of t is there's a trade-off there. If you choose a small value, you're going to have less memory, and you're going to have longer time to do the calculation, because the log is to the base 2, and you might be doing more disk reads or writes, because if you modify something and you want to put it also on the disk, it is write. For when t is very large, the index is dense, it will have more memory usage, but it will have less amount of time in terms of reads and writes to the disk. But again, it doesn't mean that we should go always with the largest t possible, because we can be wasting space in terms of we have t being, or 2t minus 1 being, or 2t is 2000, but for many nodes we can be just utilizing, let's say, 1000 or 1100 keys and so on, which is wasting so much space.